So in this video, I'm going to explain about RSA algorithm, which is one of the important algorithm in cryptography. This is one of the first successful responses to the challenges, which was developed in 1977 by Ron Rivers. That is me and the Lennon Max at the MIT, and the first published in 1978. So, because of the name of the developers, the algorithm was called as reverse distributed development (RSD), which is used widely accepted and implemented general purpose approach to public encryption algorithm. The RSD string is a block cipher in which the plain text and the ciphertext are only integers between some 0 to n minus 1 value. The typical size of a N is 1024 bits or 309 decimal digits. That is, n is less than 21024. RSA make use of an expression with exponentials. So plain text is encrypted in blocks, and each block is having a binary value which is less than some number n. That is, the block size must be less than or equal to log n plus 1 disk. For this algorithm to be satisfactory for public key encryption, the following requirements must be met. It is possible to find values of E, D, and N such that m power ed mod n is equal to capital M for all m less than n. It is relatively easy to calculate m power e mod n and c power d mod n for all values of m less than n. It is infeasible to determine d given e and n. This is the general algorithm of RSA. The steps, each step I will explain one by one. As the first step, we have to select P and Q, where P and Q are prime numbers and P is not equal to Q. Then we have to calculate n value, which is equal to multiplying P and Q, and we have to calculate pi of n, which is equal to P minus 1 into Q minus 1. And then we have to select the integer value E such a way that GCD of pi of n comma e is equal to 1, where 1 less than e less than pi of n. In such a way, you have to select the integer value e. Then we have to calculate the d value, which is equal to congruent to e inverse mod pi of n. The public key afterwards, from the calculations, we can determine the public key, which is denoted as PU is equal to E comma N, and the private key PR is equal to D comma N. Once we have determined the public key and the private key, both the sender and the receiver can calculate the plain text and then the ciphertext. For example, the encryption by Bob with Alice public key is denoted like this. Plain text m less than n, and the ciphertext is produced as m power e mod n. The decryption process by Alice with Alice public key is denoted as the ciphertext is denoted as C, and the plain text m is equal to C power d mod n. The ingredients of RSA algorithm are P and Q, two prime numbers. It's private and chosen by the sender and the receiver. N is equal to P into Q, which is public and calculated. E, which is calculated as GCD of pi of n comma E is equal to 1. It is public and chosen. And then D congruent to E inverse mod pi of n, which is private and is calculated. The encryption, A obtains B's public key and the message M is an integer in the interval 1, n minus 1. Then compute C congruent to M power E model, and then send the ciphertext C to the intended recipient B. The decryption process is all about recovering the plain text M from the ciphertext C. So B uses his private key D to recover M congruent to C power D model. This is one of the simple examples for say algorithm. For our discussion, we have chosen P as 17 and Q is equal to 11. So that N is equal to P into Q, which is equal to 187. And then pi of N is equal to P minus 1 into Q minus 1. So that is 16 into 10 is equal to 160. Then we have to select E such that E is relatively prime to pi of N, which is equal to 160 and should be less than pi of N. So that we have to, I select E as 7 and then determine D such that D into E congruent to 1 mod 160 and D should be less than 160. The correct value is D is equal to 23 because 23 into 7 is equal to 161. If you apply mod 160, then it will produce the remainder 1. So D can be calculated using the extended equatorial algorithm also. So the resulting keys are public key P is equal to 7, 187 and private key PR is equal to 23, 187. So that we can calculate C as 88 power 7 mod 187. This can be calculated by using modular arithmetic. Equal to 88 power 7 mod 187. The last row indicates that its resultant value is 11. So for decryption, you have to calculate M is equal to 11 power 23 mod 187. Again, we can use modular arithmetic to find out the resultant value of 11 power 23 mod 187, which is equal to 88. So we get the original plain text. Suppose A wants to send the following message to P. However, then it should be calculated by using the messages like n is equal to 1943 is equal to 29.67 and then pi of n is equal to 1848. Suppose he picks E as 701, then D is equal to 29 and then M1 is equal to PO, which is equal to 15.26 plus 14 is equal to 404 and M2 is equal to WE, which is equal to 22.26 plus 4 is equal to 576. M3 is equal to RE, which is equal to 17.26 plus 0 is equal to 42. So that ciphertext 1 C1 is equal to 404 power 701, which is equal to 1419 mod 1948. Similarly, EA can calculate C2 is equal to 344 and C3 is equal to 210. Now C1 is equal to 1419, which is equal to 2.26 over 2 plus 2.26 plus 15, which is equal to CCP. C2 is equal to 344, which is equal to 13.26 plus 6 is equal to NG, and C3 is equal to 210, which is equal to 8.26 plus 2, that is IC. Therefore, the ciphertext is CCPL The security of RSA is how to attack RSA algorithm. If we have n and pi of n, then we can factor n, and if you have e and d, then we can factor n also. There are various attacks posed against RSA, like unknown digits attack, low exponent attack, short range attack, timing attack, and factoring. Timing attack. Within RSA computation, we do perform exponentiation, quick exponentiation procedure, multiplication circle for each bit of the exponent, that is 1. These multiplication take random amounts of time, and it's very hard in practice, but initiated by. But we'll continue the next topic in the next video. Thank you.